Right now, as you listen to this, you believe something about time that physics has proven wrong. You believe that 1 second for you is the same as 1 second for everyone else. That time flows at the same rate for an astronaut orbiting Earth, for a clock sitting on the surface of a neutron star, and for you standing right where you are. It feels obvious. It feels like the most basic fact about reality. But it isn't true. Over a century ago, Albert Einstein showed that time is not universal. It bends. It stretches. It runs at different speeds depending on how fast you're moving and how strong the gravity around you is. And these aren't philosophical ideas. They've been measured with atomic clocks so precise they can detect the difference in time between the floor and the ceiling of a single room. Your time is not my time, and by the end of tonight, you're going to understand exactly why. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something so fundamental, so woven into your daily existence, that you've probably never once stopped to question it. Time. You wake up in the morning, you check a clock. It tells you it's 7:15. You go about your day, making appointments, catching buses, showing up to meetings. Everything runs on time. Your phone, your watch, the clock on the wall at your office, the clock on the microwave in your kitchen. They all agree. And if you called someone on the other side of the planet and asked them to compare clocks, adjusting for time zones, they would agree too. 1 second for you is 1 second for them. Time, as far as you can tell, flows at the same steady rate for everyone, everywhere. It never speeds up. It never slows down. It just ticks forward, evenly and predictably, carrying everything with it. This feels like the most obvious fact in the universe. It's so obvious that for most of human history, nobody even thought to question it. Time was just the background to everything else. Things happened, and time measured when they happened. It was like a river flowing at a constant speed, carrying all of us along at exactly the same rate. No matter who you were, no matter where you stood, no matter how fast you were moving, the river of time carried you forward at the same pace as everyone else. And this intuition isn't wrong in your everyday life. For everything you will ever experience as a human being, walking around on the surface of the Earth, this picture of time works perfectly. Clocks agree, schedules function. Physics, at human speeds and human scales, behaves as if time is universal. The difference between your time and the time experienced by someone driving past you on the highway is so vanishingly small that no watch or clock or timer in your possession could ever detect it. So, from your perspective, time really does appear to be the same for everyone. Isaac Newton, one of the greatest scientific minds in history, took this intuition and built it into the very foundation of physics. In 1687, Newton published his masterwork, the Principia, laying out his laws of motion and his law of universal gravitation. These laws described how objects move, how forces act, how planets orbit. And they worked. They worked spectacularly well. Newton's physics could predict the motion of cannonballs, the orbits of moons, the trajectories of comets. For over 200 years, Newtonian physics was the gold standard of science, the most successful description of nature ever devised. And at the heart of Newton's physics was a specific assumption about time. Newton wrote that absolute, true, and mathematical time flows equally without regard to anything external. those are close to his actual words. Time, in Newton's framework, was a fixed backdrop. It existed independently of matter, independently of space, independently of anything happening in the universe. It didn't care about you. It didn't care about the planets. It didn't care about anything. It just flowed, uniformly and eternally, the same everywhere and for everyone. This is what physicists call absolute time. It means there is one single universal clock that everything in the universe shares. 1 second on Earth is the same as 1 second on Mars, the same as 1 second near a distant star, the same as 1 second anywhere in the cosmos. You could, in principle, synchronize every clock in the universe, and they would all tick at exactly the same rate forever. No event, no motion, no force could change how fast time flows. Time was the stage on which the universe performed its drama. The actors could move around the stage, interact, collide, explode, but the stage itself never changed. It was fixed, rigid, absolute. And this framework worked. It worked for everything humans could measure for over 2 centuries. Newton's laws predicted eclipses, explained tides, described the motion of every planet in the solar system with remarkable accuracy. Engineers used them to build bridges, calculate trajectories, design machines. There was no reason to doubt that time was absolute, because every experiment, every observation, every measurement confirmed it. Or at least appeared to confirm it. But there was a problem hiding in plain sight, and it had to do with light. In the late 1800s, physicists began studying the nature of light more carefully. James Clerk Maxwell, a Scottish physicist, had unified electricity and magnetism into a single theory called electromagnetism in the 1860s. His equations predicted that electromagnetic waves should travel at a specific speed. And when he calculated that speed from the properties of electricity and magnetism, the number he got was approximately 300,000 kilometers per second. That happened to match the measured speed of light exactly. Maxwell realized that light was an electromagnetic wave. It was the same phenomenon as radio waves, infrared radiation, ultraviolet light, just at different frequencies. And his equations insisted it always traveled at the same speed in a vacuum. But here's what troubled physicists. If light is a wave, what is it waving through? Sound waves travel through air. Ocean waves travel through water. Every wave they knew about needed a medium, something physical to carry it. So they assumed light must travel through some invisible substance, filling all of space. They called it the luminiferous ether. And if the ether existed, then Earth must be moving through it as it orbits the Sun. That motion should affect the speed of light, depending on whether you measured it in the direction of Earth's motion or perpendicular to it. Think of it like swimming in a river. If you swim with the current, you move faster relative to the riverbank. If you swim against it, you move slower. If you swim across it, the result is somewhere in between. Light traveling through the ether should behave the same way. In 1887, 2 American physicists named Albert Michelson and Edward Morley designed an ingenious experiment to detect this effect. They built a device called an interferometer that split a beam of light into 2 paths, one aligned with Earth's motion and one perpendicular to it. The 2 beams traveled their separate paths and then recombined. If one path took slightly longer because it was fighting the ether current, the recombined light would show a specific interference pattern. Michelson and Morley expected to see this pattern clearly. They expected to detect Earth's motion through the ether. They ran the experiment with extraordinary care and extraordinary precision. and they found nothing. No difference. No ether wind. No matter what direction they pointed the instrument, no matter what time of year they measured, the speed of light was exactly the same in every direction. This result was baffling. It suggested that either the ether didn't exist, or something very strange was happening with the speed of light. Physicists struggled with this result for nearly 2 decades. Several brilliant thinkers, including the Dutch physicist Hendrik Lorentz and the French mathematician Henri Poincaré, developed mathematical frameworks that could accommodate the result. They proposed that objects physically contract in the direction of motion and that clocks slow down. But these were treated as mathematical tricks, adjustments to save the theory. Nobody quite understood what these adjustments meant physically. It took a young patent clerk in Bern, Switzerland, to see what the Michelson-Morley result really meant. In 1905, Albert Einstein published a paper titled "On the Electrodynamics of Moving Bodies." In it, he proposed something radical. He said the Michelson-Morley result wasn't a puzzle to be explained away. It was a fundamental truth about the universe. The speed of light in a vacuum is the same for every observer, regardless of how they are moving. It doesn't matter if you're standing still, flying in a jet, or hurtling through space at half the speed of light. When you measure the speed of a beam of light, you will always get the same answer. Approximately 300,000 kilometers per second. Always. For everyone. No exceptions. Einstein elevated this from a strange experimental fact into a principle, a foundational law of physics. And then he worked out the consequences. This might not sound revolutionary at first, but think carefully about what it implies. Imagine you're standing on a platform, watching a train pass by at 100 kilometers per hour. Someone on the train throws a ball forward at 20 kilometers per hour relative to the train. From your perspective on the platform, the ball is moving at 120 kilometers per hour. The speeds add together. This is how velocities work in everyday life and in Newton's physics. It's simple arithmetic. It's obvious. Now, replace the ball with a beam of light. Someone on the train turns on a flashlight and shines it forward. In Newton's physics, you should see that light moving at the speed of light plus 100 kilometers per hour. The velocities should add, just like with the ball. But Einstein said, no. You see the light moving at exactly the speed of light. Not the speed of light plus the train's speed, just the speed of light. The same speed the person on the train measures. The same speed you would measure if you were standing still and shining your own flashlight. The same speed everyone in the universe measures, no matter how they're moving. How can this possibly work? If 2 observers moving at different speeds both measure the same beam of light and both get the same speed, something else has to give. Speed is calculated by dividing distance by time. If the speed comes out the same for both observers, despite their different motions, then either the distances they measure must be different, or the times they measure must be different, or both. And that is exactly what Einstein showed. Both are different. Space contracts in the direction of motion, and time dilates. Time runs at different rates for observers in relative motion. The faster you move relative to someone else, the slower your time runs from their perspective. This was Einstein's theory of special relativity. And it didn't just change physics, it changed the meaning of time itself. Let me be clear about what this means. This is not a trick. This is not an error in measurement. This is not some psychological effect where time merely feels different. This is physical reality. If you are moving fast relative to me, your clocks genuinely tick slower than mine. Your heartbeats take longer. Your chemical reactions proceed more slowly. Every physical process in your body and in your environment runs at a reduced rate as measured from my frame of reference. Time itself passes more slowly for you. Not because something is wrong with your clocks, but because time is actually flowing at a different rate along your path through the universe. There's a thought experiment that makes this vivid. Imagine a clock that works by bouncing a pulse of light between two mirrors. One mirror sits on the floor, the other on the ceiling. The light bounces up, hits the top mirror, bounces back down, hits the bottom mirror. Each round trip counts as one tick of the clock. If the distance between the mirrors is fixed, the time for each tick is simply the distance divided by the speed of light. It's a beautifully simple clock. Now, put this light clock on a spaceship moving past you at tremendous speed and watch it from outside. From your perspective, the light pulse isn't just bouncing straight up and down anymore. Because the ship is moving sideways, the light has to travel at an angle. It moves up and forward to reach the top mirror, which has shifted ahead by the time the light arrives. Then it moves down and forward to reach the bottom mirror, which has also shifted ahead. The light traces a longer, diagonal zigzag path instead of a short vertical one. And here's the key. The speed of light is the same for you as it is for the person on the ship. Light doesn't speed up to compensate for the longer path. It travels at exactly 300,000 kilometers per second regardless. But the zigzag path is geometrically longer than the straight vertical path. If the light travels at the same speed, but covers a longer distance, then each tick of the moving clock takes longer to complete. The moving clock ticks slower. Time on the ship passes more slowly than time for you. The person on the ship doesn't notice anything unusual. From their perspective, they're stationary and you're the one moving past them. Their light clock bounces straight up and down as it always does. Their seconds feel like perfectly normal seconds. Their heartbeat feels normal. Their thoughts flow at the usual pace. Everything inside their ship operates exactly as expected. It's only when the two of you compare your clocks that you see the difference. Your clocks disagree, and neither one is wrong. Both are measuring time correctly for their own frame of reference. Time simply passes at different rates for the two of you because you're in relative motion. The mathematics describing this effect involves what physicists call the Lorentz factor. At everyday speeds, the effect is negligibly small. If you're driving on a highway at 100 kilometers per hour, the time dilation between you and someone standing still is so fantastically tiny that you would need to drive continuously for billions of years before your clocks disagreed by even 1 second. At airplane speeds, roughly 900 kilometers per hour, the effect is slightly larger, but still incredibly small, a matter of nanoseconds over hours of flight. At 10% of the speed of light, time runs about 0.5% slower for the moving observer. Still subtle. But as you approach the speed of light, the effect becomes dramatic. At 90% of light speed, time runs about 2.3 times slower for the moving observer. At 99% of light speed, time runs about 7 times slower. At 99.9%, about 22 times slower. And as you push closer and closer to light speed, the dilation grows without bound. If you could somehow reach the speed of light itself, which is impossible for anything with mass because it would require infinite energy, time would stop entirely. A photon, a particle of light, experiences no passage of time whatsoever. From a photon's perspective, if a photon could have a perspective, the moment of its creation and the moment of its absorption happen simultaneously. It doesn't matter if the photon travelled from a distant star for 100 years by our measurement. For the photon, no time passed at all. Now, all of this might sound like a beautiful theoretical framework, a clever thought experiment built on elegant mathematics. But the question that matters most is whether it actually happens, whether time really does slow down for objects in motion, whether the universe genuinely works this way, or whether Einstein simply wrote down a compelling story. The answer is yes, it happens. and we've confirmed it in multiple independent ways with extraordinary precision. One of the most elegant confirmations comes from particles called muons. Muons are subatomic particles similar to electrons, but about 207 times heavier. They're created naturally when cosmic rays, high-energy particles streaming in from deep space, collide with atoms in Earth's upper atmosphere at altitudes of roughly 15 to 20 kilometers above the surface. These collisions produce showers of particles, and muons are among the most common products. Here's the problem. Muons are unstable. They decay with a half-life of about 2.2 microseconds. That means after 2.2 millionths of a second, half of any group of muons will have decayed into other particles. After another 2.2 microseconds, half the remainder decay, and so on. Even traveling at 98% of the speed of light, which is a typical speed for these atmospheric muons, a simple calculation shows a muon should only be able to travel about 660 meters before decaying. That's less than half a mile. The surface of the Earth is 15 to 20 kilometers below where they're created. That's more than 20 times farther than they should be able to travel in their brief lifetimes. And yet, we detect enormous numbers of muons at the surface of the Earth. They arrive at ground level in abundance. Detectors pick them up constantly. They pass through your body at a rate of roughly 1 muon per square centimeter per minute, right now, as you listen to this. Millions of muons are raining down through you every hour. How do they survive the journey? How do they travel more than 20 times farther than their lifetime should allow? The answer is time dilation. From our perspective standing on the ground, the muons are moving at nearly the speed of light. At 98% of light speed, time for the muon runs about 5 times slower than our time as measured from our frame of reference. The muon's internal clock is ticking more slowly than ours. So its 2.2 microsecond lifetime, as measured by our clocks, stretches to about 11 microseconds. At even higher speeds, the effect is more dramatic. At 99.5% of light speed, the Lorentz factor is about 10. The muon's effective lifetime from our perspective stretches to about 22 microseconds. At these speeds and with these extended lifetimes, muons can easily cover the 15 to 20 kilometers between the upper atmosphere and the ground. The key point is this. We can measure how many muons are created in the upper atmosphere using balloon experiments and high-altitude detectors. We can measure how many arrive at the surface, and the numbers match the predictions of special relativity with time dilation precisely. They do not match the predictions of classical physics without it. Without time dilation, barely any muons would reach the ground. With time dilation, the observed numbers are exactly what Einstein's equations predict. This has been confirmed repeatedly and consistently since the 1940s. It isn't theory waiting for confirmation, it is confirmed fact. Particle accelerators provide even more direct evidence. In facilities like CERN, particles are accelerated to speeds extremely close to the speed of light. At these speeds, unstable particles live far longer than their rest frame lifetimes. This is not a subtle effect that requires statistical analysis to detect. Muons in a storage ring traveling at 99.94% of light speed live about 29 times longer than muons at rest. The measurements match special relativity's predictions to within fractions of a percent. This isn't a minor correction. It's a factor of 29. Without time dilation, particle accelerators would not function the way they do. The engineering design of these massive machines depends on time dilation being real and being precisely described by Einstein's equations. Perhaps the most direct and intuitively striking test came in 1971. Two physicists, Joseph Haefel and Richard Keating, took 4 cesium atomic clocks, among the most precise timekeeping devices available at the time, and placed them on commercial airline flights. 2 sets of clocks flew around the world. One set flew eastward with the direction of Earth's rotation. The other set flew westward against it. A third set of identical clocks stayed on the ground at the United States Naval Observatory in Washington. When the flying clocks were brought back and compared with the ground clocks, they disagreed. The clocks that had flown eastward, which were moving faster relative to Earth's center because their flight speed added to Earth's rotational speed, had lost time compared to the ground clocks. The clocks that had flown westward, which were effectively moving slower relative to Earth's center because their flight speed partially cancelled Earth's rotation, had gained time. The differences were measured in nanoseconds, billionths of a second. But they were real, they were measurable, they were repeatable, and they matched the predictions of Einstein's relativity. This experiment has been repeated many times since then, with increasingly precise equipment, and every single time the results confirm what Einstein predicted. Moving clocks tick at different rates than stationary clocks. The effect is real, physical, and measurable. It is not a theory in the colloquial sense of being an unproven guess. It is a confirmed feature of how the universe operates, tested to extraordinary precision across decades of experiments. Let me bring this into human terms using what physicists call the twin paradox. Imagine two identical twins born on the same day. One stays on Earth, the other boards a spacecraft and travels to a star 4 light-years away at 90% of the speed of light, then turns around and comes back at the same speed. The round trip covers 8 light-years of distance at 90% of light speed. From Earth's perspective, the journey takes about 8.9 years. But the travelling twins' clock runs slower because of time dilation. At 90% of the speed of light, the Lorentz factor is about 2.3. So while about 8.9 years pass on Earth, only about 3.9 years pass for the travelling twin. When the spacecraft returns and the twin steps out, they are roughly 5 years younger than their sibling who stayed home. They've aged less. Their biological clock, every cell in their body, every chemical reaction, every heartbeat, all of it ran slower during the journey. The travelling twin genuinely experienced less time. The twins would look different. The one who stayed on Earth would have 5 more years of aging, 5 more years of memories, 5 more years of lived experience. They diverged in time even though they started at the same moment and reunited at the same moment. The flow of time was physically different for each of them because their paths through the universe were different. This is not a paradox in the sense of being a logical contradiction. It's called a paradox because it seems to contradict common sense. Your intuition screams that time should be the same for both twins. How could one person age more slowly than another? But your intuition was built by evolution to handle walking speeds and local distances. It was calibrated for a world where nothing moves faster than a running animal. It was never designed to handle velocities close to 300,000 kilometers per second. At those speeds, the universe behaves in ways your intuition cannot anticipate. Your intuition is not wrong about your everyday world, it's simply incomplete. And this brings us to a concept that is absolutely central to understanding what time really is in modern physics. The concept of proper time. In Newton's universe, there was one universal time that everyone shared. One master clock for the cosmos. Einstein replaced that with something fundamentally different. Proper time is the time measured by a clock travelling along a specific path through the universe. It's personal. It belongs to a particular object, a particular observer, a particular trajectory. Your proper time is the time measured by a clock you carry with you wherever you go. And it depends on your path through the universe, on how fast you've been moving, and, as we'll explore next, on the gravitational fields you've passed through. There is no universal clock sitting outside the universe, ticking away at the one true rate. Different paths through the universe accumulate different amounts of proper time. The twin who travelled to a distant star and back aged less because their path through space-time accumulated less proper time than the path of the twin who stayed on Earth. Both paths are valid. Both clocks functioned perfectly. Both experiences of time are real. They're just different. The universe does not have a single shared flow of time. It has as many flows of time as there are paths through it. Newton's picture of time as a rigid, unchanging background served humanity well for over 200 years, but it was an approximation. An extraordinarily good approximation for everyday life, one that still works perfectly well for designing bridges, planning train schedules, and navigating your morning commute. But an approximation nonetheless. When you push to extreme speeds, when you measure with extraordinary precision, the approximation fails, and what you find beneath it is something more subtle, more strange, and more profound. Time is not separate from the universe. It is woven into the fabric of the universe itself. It stretches, it bends, it flows at different rates depending on how you move through space. And this is not philosophy. This is not a metaphor. This is measured, confirmed, engineering-grade physics that we rely on every single day in technologies ranging from particle accelerators to satellite navigation systems. But motion is only half the story, because Einstein didn't stop with special relativity. 10 years later, he published something even more profound, and it showed that velocity isn't the only thing that changes the flow of time. Gravity does too, and the consequences of that discovery reach even deeper than anything we've discussed so far. So far, we've seen that the speed at which you move changes how fast time passes for you. Motion through space changes your motion through time. Faster movement through space means slower passage through time. This was Einstein's theory of special relativity, and it shattered the idea that time flows at the same rate for everyone. But Einstein didn't stop there. In fact, he spent the next 10 years working on something even more ambitious. He wanted to understand gravity, not just as a force that pulls things together, but as something deeper. And what he discovered was that gravity doesn't merely attract objects toward each other. Gravity warps the very fabric of space and time. And that warping changes how fast clocks tick, not because of motion, but because of where you are. To understand how Einstein arrived at this, you need to know about a single thought experiment that he later called the happiest thought of his life. Imagine you're standing inside an elevator on the top floor of a very tall building. The cable snaps. The elevator goes into freefall. During those terrifying seconds of plummeting downward, something remarkable happens. You become weightless. Your feet lift off the floor. A coin you are holding floats beside you in midair. A cup of water floats next to your hand, with the water drifting lazily inside it. Everything in the elevator floats, as if gravity has vanished. You are falling, but from inside the elevator, with no windows, you cannot tell whether you're falling toward the ground in a gravitational field or floating freely in deep space, far from any planet or star where there is no gravity at all. The experience is identical. Now flip it around. Imagine you're in that same elevator, but now it's in deep space, millions of kilometers from any star or planet. There is no gravity here. You're floating weightlessly. But now a rocket engine attached to the roof of the elevator fires up and starts accelerating the elevator upward. Your feet press against the floor. A coin you release falls and hits the ground. A cup of water feels heavy in your hand. Everything behaves exactly as if you were standing on the surface of a planet being pulled downward by gravity. From inside the elevator, you cannot distinguish between being accelerated upward in empty space and standing still in a gravitational field. The physics is the same. Einstein realized this wasn't a coincidence or a quirk of human perception. He elevated it to a fundamental principle of nature, the equivalence principle. Gravity and acceleration are locally indistinguishable. They produce identical physical effects in every measurable way. And if they produce identical effects, Einstein reasoned, they must be aspects of the same underlying phenomenon. This insight had immediate consequences for time. We already know from special relativity that acceleration affects time. Consider a rocket accelerating through empty space. A clock at the rear of the rocket, the end closer to the engines, ticks at a slightly different rate than a clock at the front. This follows directly from special relativity and has been confirmed experimentally. The clock deeper in the acceleration field, closer to the engines, ticks slower. Now apply the equivalence principle. If acceleration and gravity are indistinguishable, then this effect must also happen in a gravitational field. A clock at the bottom of a tall building, deeper in Earth's gravitational field, must tick slower than a clock at the top. Not because something is wrong with the lower clock, not because of temperature, air pressure, humidity, or any mechanical interference. Because time itself flows at different rates at different heights in a gravitational field. This is gravitational time dilation, and it is one of the most profound predictions in all of physics. Time passes more slowly where gravity is stronger. A clock on the surface of the Earth ticks slightly slower than a clock on top of a mountain. A clock at sea level ticks slightly slower than a clock aboard a satellite orbiting high above. A clock on the surface of a neutron star ticks dramatically slower than a clock floating in empty space far from any massive object. The stronger the gravitational field you sit in, the slower your time passes as measured by someone farther from the source of that gravity. Einstein didn't arrive at this through vague reasoning or philosophical speculation. He built a complete mathematical framework called General Relativity, which he published in 1915 after a decade of extraordinarily difficult work. General relativity describes gravity not as a force that reaches across space and pulls objects together, the way Newton described it, but as a curvature in space-time itself, caused by the presence of mass and energy. Think of it this way. Imagine stretching a thin rubber sheet flat and taut like a trampoline. Now place a heavy bowling ball in the center. The sheet sags, forming a smooth, curved depression around the ball. If you roll a marble across the sheet near the bowling ball, the marble doesn't travel in a straight line anymore. It curves toward the bowling ball, following the warped surface. From above, it looks like the bowling ball is pulling the marble toward it with some invisible force. But there is no force reaching out from the bowling ball. The marble is simply following the curved geometry of the surface it's rolling on. It's traveling along the straightest possible path available to it, but because the surface itself is curved, that straightest path bends toward the heavy object. This is roughly how general relativity describes gravity. Mass and energy warp the geometry of space-time. Objects moving through warped space-time follow paths called geodesics, the equivalent of straight lines through curved geometry. The Earth doesn't orbit the Sun because an invisible thread of force connects them across 93 million miles of space. The Earth orbits because the Sun's enormous mass has curved the space-time around it, and Earth follows the straightest possible path through that curved space-time. That path happens to be a nearly circular orbit, repeating year after year. But here's the critical point most people miss. When physicists say space-time is curved, they don't just mean space is curved. Time is part of space-time. Time is woven into the fabric alongside the three dimensions of space. When mass curves space-time, it curves both the spatial dimensions and the time dimension together. And it turns out that for objects moving at everyday speeds, the curvature of time is actually far more significant than the curvature of space. The reason you feel pulled toward the ground right now, the reason you fall when you trip, the reason a dropped ball accelerates downward, is primarily because time runs at different rates at different heights. Your head exists in a region where time flows at a slightly different rate than your feet. This difference in time flow across different heights is what creates the effect you experience as the pull of gravity. That might sound bizarre, but consider what it means for an object to follow the straightest possible path through space-time when time flows at different rates at different heights. Everything moves through time. You're moving through time right now, even if you're sitting perfectly still in space. And when the rate of time differs between two nearby heights, the straightest path through space-time curves toward the region where time flows more slowly. That direction is downward, toward the source of gravity, toward the center of mass. This is what gravity is in general relativity. Not a force in the traditional sense, not something reaching out and pulling on you. It's a consequence of the geometry of space-time, and it is largely a consequence of the curvature of time. The mathematics Einstein used to express this, the Einstein field equations, are among the most complex and beautiful in all of physics. Their solutions predict specific, testable effects. Time runs slower where gravity is stronger. Light bends when it passes near massive objects. Space itself stretches and compresses in the presence of mass. The orbit of Mercury precesses at a rate slightly different from what Newton's theory predicts. Every one of these predictions has been tested. Every one has been confirmed. The first direct measurement of gravitational time dilation came in 1959. Two physicists at Harvard University, Robert Pound and Glenn Rebka, designed a beautifully straightforward experiment. They placed a source of gamma rays at the bottom of a tower in the Jefferson Physics Laboratory and a detector at the top. The tower was about 22.5 meters tall, roughly 74 feet. Not a large distance by any standard. The gravitational difference between the bottom and the top of a 74-foot tower is incredibly small. But Pound and Rebka had a technique precise enough to detect it. They used a phenomenon called the Mossbauer effect, which allows gamma rays to be emitted and absorbed at extraordinarily specific frequencies. The precision is remarkable, capable of detecting frequency changes of just a few parts in a trillion. The idea was simple. A gamma ray photon emitted at the bottom of the tower has to climb upward against Earth's gravity to reach the detector at the top. As it climbs, it loses energy. Not much, an almost unimaginably small amount, but a measurable amount. And since a photon's energy is directly related to its frequency, losing energy means its frequency decreases. The photon shifts toward lower frequencies. This is called gravitational redshift, and it is a direct consequence of gravitational time dilation. Why does gravitational redshift prove that time flows at different rates at different heights? Because frequency is just a count of oscillations per unit of time. If a photon is emitted at the bottom of the tower at a certain frequency, and that frequency appears lower when measured at the top, that means fewer oscillations arrive per second at the top than were emitted per second at the bottom. The photon itself hasn't changed during its short journey up the tower. It's the same photon. So, if fewer oscillations arrive per second, the only explanation is that seconds themselves are different at the two locations. A second at the bottom of the tower is physically shorter than a second at the top. Time ticks faster at the top of the tower than at the bottom. Gravity has slowed time down at the lower elevation. Pound and Rebka measured this effect, and their result matched Einstein's prediction. The gravitational redshift across a 22.5 meter height difference was exactly what general relativity said it should be. The initial measurement agreed to within about 10%. Subsequent refined versions of the experiment, carried out by Pound and his colleague Snyder in 1965, achieved agreement within about 1%. This was direct, laboratory-based confirmation that gravity affects the passage of time. Not at cosmic scales, not near exotic objects, right here on Earth, across a height difference shorter than the length of a swimming pool. But perhaps the most compelling evidence that gravitational time dilation is real comes from something billions of people rely on every single day without ever thinking about it. The Global Positioning System, GPS. GPS consists of a constellation of at least 24 satellites orbiting Earth at an altitude of approximately 20,200 kilometers, roughly 12,500 miles above the surface. Each satellite carries extremely precise atomic clocks. The system works by having your GPS receiver, the chip inside your phone or your car's navigation unit, pick up signals from multiple satellites simultaneously. Each signal carries information about which satellite sent it, and exactly when the signal was transmitted, according to that satellite's onboard clock. Your receiver compares the arrival times of signals from different satellites and uses the tiny differences to calculate your position through a process of triangulation. The precision required for this to work is extraordinary. Light travels approximately 30 centimeters, roughly 1 foot, in a single nanosecond. To determine your position to within a few meters, the system needs timing accuracy better than about 30 nanoseconds. That is 30 billionths of a second. Any error in the satellite clocks directly translates into position error on the ground. Now here's where Einstein enters your daily life. The satellites are moving at about 3.9 kilometers per second as they orbit Earth. That's fast by everyday standards, but nowhere near the speed of light. Still, special relativity tells us that because of their orbital velocity, the satellite clocks tick slightly slower than clocks on the ground. This effect amounts to about 7 microseconds per day that the satellite clocks lose relative to ground clocks. 7 millionths of a second per day. That sounds tiny. But remember, GPS needs nanosecond precision, and 1 microsecond is 1,000 nanoseconds. 7 microseconds of timing error per day would be catastrophic for navigation accuracy. But there's a second effect working in the opposite direction. The satellites orbit at 20,200 kilometers above the surface. They're much higher up in Earth's gravitational field, where gravity is weaker. General relativity tells us that because gravity is weaker at that altitude, the satellite clocks tick faster than clocks on the ground. This effect is larger than the velocity effect. It amounts to about 45 microseconds per day that the satellite clocks gain relative to ground clocks. The two effects oppose each other. Orbital velocity makes the satellite clocks tick slower by about 7 microseconds per day. Weaker gravity at orbital altitude makes them tick faster by about 45 microseconds per day. The net result is that the satellite clocks gain approximately 38 microseconds every single day compared to identical clocks on Earth's surface. 38 microseconds sounds trivial, but light travels about 11.4 kilometers in 38 microseconds. If GPS engineers didn't correct for relativistic time dilation, position errors would accumulate at a rate of roughly 10 kilometers per day. Within a single day, your GPS would be sending you to the wrong neighborhood. Within a few days, it would be directing you to the wrong part of the city. Within a week, it would be essentially useless for anything more specific than identifying which country you're standing in. The engineers who designed GPS understood this from the beginning. The corrections for both special and general relativistic time dilation are built directly into the system. Before each satellite is launched, its onboard atomic clock is deliberately adjusted to tick at a slightly different rate than a ground clock, pre-compensating for the relativistic effects it will experience once it reaches orbit. Additional corrections are applied continuously by ground control stations monitoring the satellite network. Every position calculation your phone performs, every turn-by-turn direction, every estimated arrival time, relies on Einstein's theories of relativity being correct and being accounted for with extraordinary precision. This is not abstract theory waiting for experimental confirmation. This is working technology. Billions of people carry GPS receivers in their pockets every day. Aircraft navigate by GPS. Ships cross oceans by GPS. Emergency services locate callers by GPS. Agricultural equipment plants seeds in precise rows by GPS. Military operations depend on GPS. All of these applications function because gravitational time dilation is real and because Einstein's equations describe it with sufficient accuracy to keep the system operational. Modern atomic clocks have pushed these measurements to even more extraordinary precision. In 2010, physicists at the National Institute of Standards and Technology used aluminium-ion clocks, among the most precise timekeeping devices ever constructed, to measure gravitational time dilation across a height difference of just 33 centimeters, about the distance from your knee to your waist. They found that the higher clock ticked faster, exactly as general relativity predicted. The difference was roughly 4 parts in 100 million trillion, an almost unfathomably small number. But they measured it. They confirmed that time flows at a detectably different rate between the height of your knee and the height of your hip. Think about what that means. Right now, as you sit or stand, time is passing at a slightly different rate for your head than for your feet. Your head sits higher in Earth's gravitational field, where gravity is infinitesimally weaker. General relativity says your head ages slightly faster than your feet. Over the course of a full lifetime, say 80 years, the accumulated difference amounts to roughly 90 billionths of a second. Your feet are about 90 nanoseconds younger than your head. You will never feel this difference. No biological process in your body is sensitive to 90 nanoseconds. But it is real. It has been measured, and it follows precisely from equations Einstein wrote down over a century ago. On Earth, gravitational time dilation is subtle. The effects are genuine but tiny, detectable only with the most precise instruments humanity has ever constructed. But the universe contains objects where gravitational time dilation becomes dramatic, even extreme. And examining these objects reveals just how profoundly gravity can reshape the flow of time. A neutron star is one of the densest objects in the known universe. It forms when a massive star exhausts its nuclear fuel and its core collapses catastrophically. The core, containing roughly 1.5 to 2 times the mass of our Sun, crushes down under its own gravity into a sphere only about 20 kilometers across, about the size of a city. The density is staggering. A teaspoon of neutron star material would weigh approximately 4 billion tons if you somehow brought it to Earth's surface. The gravity at the surface of a neutron star is roughly 200 billion times stronger than the gravity you feel standing on Earth right now. At this level of gravitational intensity, time dilation becomes enormous. A clock on the surface of a typical neutron star would tick roughly 20 to 30% slower than a clock far away in empty space. This is not a nanosecond difference accumulated over decades. This is a massive, obvious discrepancy. For every 10 seconds that pass on the distant clock, only about 7 or 8 seconds pass on the neutron star's surface. Every physical process happening at that surface, every vibration of every atom, every nuclear reaction, runs noticeably slower as observed by someone watching from a great distance. If you could somehow survive on the surface of a neutron star and look outward at the universe, you would see distant stars and galaxies evolving faster than they should. Time out there would be rushing ahead relative to yours. A year of your life on that surface would correspond to more than a year passing for the rest of the cosmos. You would be aging more slowly than the universe around you, not because of your velocity, but purely because of how deep you sit in a gravitational well. But neutron stars are modest compared to the ultimate gravitational extreme: black holes. A black hole forms when mass collapses into such a compact volume that the gravitational field becomes so intense nothing can escape. Not matter, not light, not any signal of any kind. The boundary surrounding a black hole, beyond which escape becomes impossible, is called the event horizon. And at this boundary, gravitational time dilation reaches its most extreme conceivable state. As you approach a black hole from a safe distance, time dilation increases steadily. The closer you get to the event horizon, the slower your clocks tick relative to a distant observer. A distant observer watching you fall toward the black hole would see your clocks ticking slower and slower. They would see your motions becoming sluggish, as if you were moving through thickening honey. The light you emit would be redshifted to longer and longer wavelengths, growing dimmer and redder. As you approach the event horizon itself, you would appear from the outside to slow down asymptotically, approaching the boundary but never quite reaching it. You would seem to freeze. Your image would grow dimmer, redder, and eventually fade from view entirely. From the distant observer's perspective, you never cross the event horizon. You are suspended there, frozen at the boundary, fading into invisibility. But from your own perspective, falling inward, the experience is completely different. You cross the event horizon in a finite amount of time according to your own clock. You don't feel anything unusual at the moment of crossing. The horizon is not a physical wall or barrier. It's a boundary defined by space-time geometry, a point of no return. You pass through it smoothly, and your personal clock keeps ticking normally from your own point of view. The two descriptions, the outside observer's and yours, are both physically valid. They simply disagree about time. Time is that fundamentally different for observers at different depths in a gravitational field. At the center of our own galaxy, the Milky Way, sits a supermassive black hole called Sagittarius E star. It has a mass of roughly 4 million times the mass of our Sun. Its event horizon spans a diameter of approximately 24 million kilometers, about 17 times the diameter of our Sun. Stars orbit this black hole at tremendous speeds. One star, designated S2, completes a full orbit every 16 years, reaching speeds of nearly 8,000 kilometers per second at its closest approach. That is approximately 2.5% of the speed of light. At its nearest point to Sagittarius E star, S2 experiences both velocity-based time dilation from its enormous speed and gravitational time dilation from its proximity to the black hole. Astronomers have measured the gravitational redshift of light from S2 as it swings through closest approach, and the measurements match general relativity's predictions with extraordinary precision. This is direct observational evidence of gravitational time dilation occurring 26,000 light-years from Earth, around one of the most extreme gravitational environments in our galaxy. Here is what all of this tells us. Time is not a rigid, unchanging backdrop against which the universe plays out its events. Time is part of the universe. It is woven into the geometry of space-time itself. Mass and energy curve that geometry, and where the geometry is curved, time flows at a different rate. A clock near a massive object and a clock far from any massive object do not agree. They tick at different rates. They accumulate different amounts of time over the same journey. And this is not a philosophical argument or an abstract mathematical curiosity. It is measured, confirmed, engineering-grade physics. We measure it in laboratories across height differences shorter than a meter. We build corrections for it into satellite navigation systems that billions of people depend on every day. We observe it in the light from stars orbiting a supermassive black hole at the heart of our galaxy. Your time depends on where you are. It depends on the gravitational field you occupy. There is no master clock hovering outside the universe, ticking at the one true rate. Each path through space-time accumulates its own proper time. Your path is unique. Your time is yours. It agrees approximately with the time of people near you because you share approximately the same gravitational environment. But approximately is not exactly. And when the differences in gravity become large, the differences in experienced time become large too. This picture of time, arising from Einstein's general relativity, is extraordinarily successful. It describes everything from the nanosecond corrections required by GPS satellites to the extreme warping of time at the edges of black holes. It has passed every experimental test for over a century with no confirmed failures. And yet, as complete as it seems, this is not the end of the story. Because there exists another pillar of modern physics, equally well tested, equally triumphant in its own domain, that treats time in a fundamentally different and incompatible way. Quantum mechanics, the theory governing atoms and subatomic particles, does not treat time as part of a dynamic, curving space-time fabric. It treats time as something else entirely. And the tension between these two descriptions of time sits at the heart of one of the deepest unresolved problems in all of physics. General relativity paints a remarkable picture of time. Time is not a fixed background ticking uniformly for everyone. It is part of the fabric of space-time, stretched by motion, warped by gravity, flowing at different rates depending on your path through the universe. This picture has been confirmed by every experiment ever designed to test it, from particle accelerators to GPS satellites to observations of stars orbiting black holes. It is one of the most thoroughly tested ideas in the history of science. But general relativity is not the only pillar of modern physics. There is another framework, equally well tested, equally triumphant in its own domain, that describes a completely different aspect of reality: quantum mechanics. And quantum mechanics treats time in a way that flatly contradicts general relativity. Not subtly, not around the edges. The contradiction runs straight to the foundations of both theories. To understand this conflict, you first need to understand what quantum mechanics is and why it was developed. In the early 1900s, physicists discovered that the laws governing atoms and subatomic particles were completely different from the classical laws that Newton had laid down centuries earlier. Objects at the smallest scales didn't behave like tiny billiard balls following predictable trajectories. They behaved in ways that defied common sense. An electron orbiting an atomic nucleus doesn't travel in a neat circular orbit the way a planet orbits a star. Instead, it exists in a cloud of probability, a smeared-out wave of likelihood that tells you where the electron might be found if you measure its position, but doesn't tell you where it actually is before you measure. Before measurement, the electron doesn't have a definite position. It exists in a state called superposition, simultaneously occupying many possible positions at once. When you measure it, the superposition collapses and the electron appears at a specific location. But which location it appears at is governed by probability, not certainty. You can calculate the odds of finding it here versus there, but you cannot predict the exact outcome of any single measurement. This isn't a limitation of your instruments. It isn't a matter of needing better detectors or more computing power. The uncertainty is fundamental. It is built into the structure of reality at the quantum level. Nature itself does not determine the outcome until the measurement occurs. This was deeply unsettling to many physicists when quantum mechanics was first developed in the 1920s. Albert Einstein himself never fully accepted it, famously insisting that nature does not play dice. But experiment after experiment confirmed that quantum mechanics was correct. Whatever your philosophical discomfort, the theory worked. It predicted outcomes with astonishing precision. Quantum mechanics is arguably the most successful theory in the history of science. It explains the structure of atoms, the behavior of molecules, the properties of solids and liquids and gases. It explains why metals conduct electricity and why insulators don't. It explains how transistors work, which means it underpins every computer, every smartphone, every piece of digital technology you have ever used. It explains the nuclear reactions that power the sun and stars. It explains the periodic table of elements. It explains the color of a flame, the operation of a laser, the mechanism behind an MRI scanner. Without quantum mechanics, modern technology collapses overnight. Almost everything built in the last century depends on it, and at the heart of quantum mechanics sits an equation that governs how quantum states change: the Schrödinger equation. Erwin Schrödinger published this equation in 1926, and it became the central equation of non-relativistic quantum mechanics. Understanding how time appears in this equation is essential to understanding the deep tension between quantum mechanics and general relativity. The Schrödinger equation does something specific. It takes the quantum state of a system at one moment and tells you what the quantum state will be at a later moment. You give it the state at time equals 0, and it produces the state at time equals 1 second, or 5 seconds, or any time you choose. It evolves the quantum state forward through time, smoothly and deterministically. There is nothing random about the evolution itself. The randomness only enters when you make a measurement. Between measurements, the quantum state evolves according to the Schrödinger equation in a completely predictable way. Now here is the critical detail. In the Schrödinger equation, time is not treated the same way as other physical quantities. Position, for example, is a quantum observable. In the mathematical framework of quantum mechanics, every observable physical quantity is represented by a mathematical object called an operator. Position has an operator, momentum has an operator, energy has an operator, angular momentum has an operator. These operators act on the quantum state and extract information from it. When you measure a particle's position, the mathematical description of that measurement involves applying the position operator to the quantum state. The possible outcomes of the measurement are the eigenvalues of the operator. The probabilities of each outcome are calculated from the quantum state using a specific mathematical rule. Time has no such operator in standard quantum mechanics. There is no time operator. You cannot apply a mathematical object to a quantum state and extract the time of the system the way you extract its position or its momentum. Time is not something you measure within quantum mechanics. Time is something you read from an external clock that exists outside the quantum system. The Schrödinger equation evolves the quantum state as a function of time, but time itself is fed into the equation from outside. It is a label, a parameter, a tag that tells you which moment you are asking about. It is not a dynamical variable that the quantum system determines or influences. Think of it this way. Imagine watching a movie on a screen. The images on the screen change from frame to frame. The actors move, the scenery shifts. Everything within the movie evolves and changes. But the clock that advances the movie from one frame to the next is not part of the movie. It is the projector mechanism. It sits outside the film, ticking forward at a steady rate, pulling each frame into view. The characters in the movie don't control the clock. They don't experience it. They don't interact with it. The clock just runs, and the movie unfolds according to it. In quantum mechanics, the quantum state is like the movie. It changes and evolves. But time is like the projector. It sits outside the system, ticking uniformly, advancing the state forward. The quantum system doesn't shape time. Time shapes the quantum system. This is a profound asymmetry. In quantum mechanics, space and time are not treated equally at all. Position is something the system has and something you can measure. Time is something the system moves through, dictated by an external parameter that nothing within the system can alter. You can ask, what is the probability of finding this particle at position X? That is a perfectly well-defined quantum mechanical question with a precise mathematical answer. But you cannot ask, in the same framework, what is the probability of finding this particle at time t? Time is not an outcome of measurement in quantum mechanics. It is the backdrop against which measurements occur. There is a subtlety here that deserves attention. You may have heard of the energy-time uncertainty principle. It sounds parallel to the position-momentum uncertainty principle that Heisenberg formulated in 1927. The position-momentum uncertainty principle says you cannot simultaneously know a particle's exact position and its exact momentum. The more precisely you know one, the less precisely you can know the other. This is a genuine, fundamental relationship between two quantum observables, both represented by operators. The energy-time relationship looks similar on the surface. It says that the uncertainty in energy multiplied by the uncertainty in time must exceed a certain minimum value. But the meaning is different. In the position-momentum case, both position and momentum are quantum observables with operators. In the energy-time case, energy is a quantum observable with an operator, but time is not. The uncertainty in time in this context does not mean the same thing as uncertainty in position in the other case. It refers to something more like the time it takes for the quantum state to change noticeably. It is a measure of how quickly a system evolves, not a fundamental uncertainty in the time coordinate itself. This distinction matters because it highlights that time occupies a unique and privileged role in quantum mechanics. It is not just another variable like position or momentum. It is structurally different. It is the one thing in the theory that does not get the full quantum treatment. Everything else in quantum mechanics, every particle, every field, every physical property, is subject to quantum uncertainty, quantum superposition, quantum measurement. But time is exempt. Time just ticks along, untouched and unaffected by the quantum weirdness happening around it. And here is the thing. Within the domain where quantum mechanics is applied, this approach works flawlessly. When you are studying atoms, molecules, subatomic particles, condensed matter systems, quantum optics, anything governed by quantum mechanics, in a region where gravity is weak and space-time is approximately flat, treating time as an external parameter produces spectacularly accurate predictions. There is no practical problem with it. The experiments agree. The technology works. The calculations match observations to many decimal places. The problem emerges only when you try to combine quantum mechanics with general relativity. Because in general relativity, time is not an external parameter at all. Time is a dynamical part of the physical system. Space-time is not a fixed stage. It curves and stretches and evolves in response to the matter and energy it contains. Time is woven into the fabric of reality alongside space. Mass tells space-time how to curve, and space-time tells matter how to move. Time is not outside the system watching it unfold. Time is part of the system. It participates, it responds, it changes. So you have two extraordinarily successful theories that disagree about the most fundamental aspect of time's nature. In quantum mechanics, time is a rigid, fixed, external backdrop. In general relativity, time is a flexible, dynamic, physical entity. Both theories are correct within their respective domains. Both have been tested to extraordinary precision. But they cannot both be fundamentally right about time's nature at the deepest level. Somewhere, at some scale, in some regime, one or both of these descriptions must break down and be replaced by something deeper. That regime is quantum gravity. The scale where both quantum effects and gravitational effects are significant simultaneously. This happens at the Planck scale, distances and times so unimaginably small that our current theories cannot describe them. At the Planck scale, you need a theory that is both quantum mechanical and gravitational. You need a theory where space-time itself is subject to quantum rules. And when physicists tried to construct such a theory, they ran into one of the deepest and most disturbing problems in all of fundamental physics. Time vanished. The story begins with a straightforward question. If quantum mechanics applies to everything, shouldn't it apply to space-time itself? After all, quantum mechanics governs atoms. It governs electromagnetic fields. It governs the nuclear forces. Why should gravity and space-time be exempt? If space-time is a physical entity, a dynamical thing that curves and evolves, then it should be subject to quantum mechanics just like everything else. In the 1960s, physicists John Archibald Wheeler and Bryce DeWitt attempted to do exactly this. They took Einstein's equations of general relativity, which describe how space-time curves in response to matter and energy, and tried to apply the standard techniques of quantum mechanics to them. The goal was to write down the quantum version of Einstein's equations. an equation that describes not a single definite space-time geometry, but a quantum superposition of all possible geometries. An equation whose solutions would be the quantum state of the entire universe, including space-time itself. What they produced is now called the Wheeler-DeWitt equation, and it has a deeply unsettling feature. There is no time in it. The equation contains no time variable. It does not describe how anything evolves from one moment to the next. It does not advance a quantum state forward through time the way the Schrödinger equation does. Instead, it simply states a constraint. The quantum state of the universe must satisfy a certain mathematical condition. That condition relates the geometry of space to the matter and energy content, but it does so without any reference to time whatsoever. In the Schrödinger equation, there is a term involving the rate of change of the quantum state with respect to time. That term is what makes the equation an evolution equation. It tells you how the state changes as time progresses. In the Wheeler-DeWitt equation, that term is absent. It is not hidden or simplified. It is genuinely not there. The equation says, in essence, that the total energy of the universe, including gravitational energy, is zero, and it says this timelessly. There is no before and after. There is no earlier and later. There is just a static mathematical condition that the quantum state must satisfy. This is sometimes described by saying that the Wheeler-DeWitt equation predicts a frozen universe. A universe where nothing changes, nothing evolves, nothing happens. The equation describes a quantum state that simply exists, complete and unchanging, like a block of ice rather than a flowing river. There is no flow, there is no direction, there is no passage. The equation treats the universe as a single, timeless object. This result shocked physicists. It didn't match reality at all. We obviously experience time. Things change, events happen, causes precede effects. Tomorrow is different from yesterday. How can the fundamental equation of quantum gravity predict a universe without time when we so clearly live in a universe with time? This puzzle has become known as the problem of time, and despite decades of effort by hundreds of brilliant physicists, it remains one of the deepest unsolved problems in theoretical physics. The problem is not simply a matter of finding better mathematics or more clever approximations. It strikes at the conceptual foundations of what time is and where it comes from. There are multiple facets to the problem. One facet is the frozen formalism problem. How do you recover the appearance of change and evolution from an equation that has no time? If the fundamental description of the universe is timeless, how does the flowing, changing, unfolding world we experience emerge from it? Where does the illusion of temporal flow come from if the deepest level of reality has no time at all? Another facet is the multiple choice problem. In general relativity, there are many different ways to slice space-time into space and time. You can define now in many different ways, and each choice leads to a different notion of time. These different choices are all equally valid in general relativity. The theory doesn't prefer one over another. But in quantum mechanics, you need to pick a time variable to write down the Schrödinger equation. Which time do you choose? And does the physics depend on your choice? If it does, the theory has a serious problem, because physical predictions shouldn't depend on arbitrary choices you make. A third facet is the inner product problem. In quantum mechanics, probabilities are calculated using a mathematical structure called an inner product. This structure depends on having a well-defined notion of time. Without time, the standard probabilistic interpretation of quantum mechanics breaks down. You cannot easily assign probabilities to outcomes when there is no temporal ordering to distinguish a measurement from its result, no before and after, no preparing a system and then observing it. Physicists have proposed many approaches to resolving the problem of time. None has achieved universal acceptance. Each has insights, and each has difficulties. One approach, associated with the physicist Julian Barbour, takes the timelessness of the Wheeler-DeWitt equation at face value. Perhaps time really doesn't exist at the fundamental level. Perhaps what we call time is an emergent phenomenon, arising from correlations between physical variables, rather than from any fundamental temporal flow. In this view, the universe is a vast collection of static configurations. Each configuration is a possible arrangement of all the matter and geometry in the universe at a single instant. The Wheeler-DeWitt equation constrains which configurations are physically allowed. Time is not fundamental. It appears when you compare one configuration to another and notice that they are related in a way that looks like evolution. Think of a row of photographs laid out on a table. Each photograph shows a scene at a particular moment, a ball at different heights, a clock showing different readings, a person in different positions. None of the individual photographs contains time. Each one is static. But when you lay them out in order and compare them, you see a pattern that looks like change. You see the ball falling, the clock ticking, the person walking. The appearance of time emerges from the correlations between the photographs, not from any flow within any single photograph. Barbour suggests reality might be like this: a collection of timeless moments with the experience of time arising from how those moments relate to each other. Another approach, developed by Don Page and William Wouters in the 1980s, proposes that time can be recovered from the timeless Wheeler-DeWitt equation through conditional probabilities. The idea is this: within the quantum state of the universe, you can ask relational questions. Not what happens at time t, because there is no external time, but instead, if a particular clock within the universe shows a particular reading, what do the rest of the variables look like? Time is not read from an external clock sitting outside the universe. It is read from a physical subsystem within the universe, a clock that is itself part of the quantum state. The passage of time is then defined relationally. Time is what a clock measures, not an abstract background parameter, but a physical correlation between one part of the universe and another. This is a subtle but important shift. In standard quantum mechanics, time is external to the system. In the Page-Wouters approach, everything is internal. The universe as a whole is timeless, satisfying the Wheeler-DeWitt equation, but subsystems within the universe can serve as clocks for other subsystems. Time emerges from internal correlations, not from external parameters. Recent experiments using quantum systems in laboratories have actually tested aspects of this idea and found results consistent with it. A pair of entangled particles can be set up so that one serves as a clock for the other. From outside the entangled pair, the system is static, but from within, one particle's evolution can be described as occurring in time measured by the other particle. Still another perspective comes from attempts to build a full quantum gravity theory from scratch, rather than trying to quantize classical general relativity directly. In loop quantum gravity, for example, space is built from discrete quantum units. Time in this framework arises from the transitions between quantum states of geometry. There are no smooth, continuous time flows. Instead, there are discrete quantum jumps from one spatial configuration to another. The ordering and structure of these jumps produce what we experience as the passage of time. Time is not a parameter fed in from outside. It is generated by the quantum dynamics of space itself. In string theory, the situation is different again. String theory is typically formulated in a fixed background spacetime, which means time is treated as a parameter much as it is in ordinary quantum mechanics. But string theorists argue that the background dependence is an artifact of how the theory is currently formulated, not a fundamental feature. The full, non-perturbative version of string theory, if it could be completely understood, might not require a fixed background space-time at all. Time might emerge from the theory rather than being put in by hand. But this remains an aspiration rather than an accomplished result. Each of these approaches captures something potentially important. Each has been developed with mathematical rigor, but none has produced a complete, universally accepted resolution to the problem of time. The problem remains open. It is one of the central obstacles standing between us and a full theory of quantum gravity. And this is what makes the nature of time so fascinating and so humbling. We have two extraordinarily successful theories of physics. General relativity describes time as a dynamic part of the physical universe, curved by mass and energy, flowing at different rates in different places. Quantum mechanics describes time as an external parameter, a fixed background clock that ticks uniformly while everything else in the universe fluctuates and superposes and interferes. Both theories are confirmed by overwhelming experimental evidence, but their descriptions of time are incompatible. They cannot both be right at the deepest level. The resolution, whatever it turns out to be, will almost certainly transform our understanding of what time actually is. It may reveal that time is not fundamental at all, but emerges from something deeper. It may reveal that time has a quantum structure we haven't yet imagined. It may reveal connections between time, information, and entropy that we currently only glimpse in outline. Whatever the answer, it will be one of the most profound discoveries in the history of science. What we know for certain is this: the everyday experience of time, the sense of a universal clock ticking identically for everyone, is not how the universe works. Relativity showed us that time depends on motion and gravity. Quantum mechanics treats time as an external parameter, fundamentally different from the dynamic space-time of general relativity. And when you try to combine these two pillars of physics into a single framework, time itself becomes the deepest puzzle. It isn't that time is an illusion. The effects of time, the differences in aging, the ticking of clocks, the evolution of quantum states, these are all physically real. But the nature of time, what it is at the most fundamental level, whether it is a basic ingredient of reality or something that emerges from a deeper, timeless structure, this remains genuinely unknown. And that unknown sits at the very frontier of human knowledge, waiting to be explored. We've now reached the frontier. We've seen that relativity describes time as a dynamic part of space-time, curved by mass and energy, flowing at different rates depending on where you are and how you move. We've seen that quantum mechanics treats time as a fixed external parameter, a background clock ticking uniformly while quantum states evolve. And we've seen that when you try to combine these two frameworks, time itself becomes the deepest puzzle in physics. The Wheeler-DeWitt equation, the closest thing we have to a quantum equation for the universe, contains no time at all. This is not a minor technical difficulty. It strikes at the most basic question you can ask about time. What is it, really? To make progress, physicists need a theory of quantum gravity, a framework that consistently incorporates both quantum mechanics and general relativity. Such a theory would describe what happens at the Planck scale, where distances and times are so small that both quantum effects and gravitational effects are significant simultaneously. At this scale, roughly 10 to the negative 35th meters in distance and 10 to the negative 43rd seconds in time, our current theories break down completely. Space-time as we know it may not exist in any recognizable form, and whatever replaces it would determine, once and for all, whether time is fundamental or emergent, whether it is continuous or discrete, whether it has a beginning or is eternal. No complete theory of quantum gravity exists. This is one of the most important unsolved problems in all of science. But there are several candidate frameworks, each offering a different perspective on what time might be at the deepest level. And these frameworks don't just disagree on technical details, they disagree on whether time is real. Loop quantum gravity, developed primarily by Carlo Rovelli, Lee Smolin, and others beginning in the late 1980s, proposes that space is not continuous. Instead, space is built from discrete quantum units, tiny chunks of volume connected by links that carry information about area. These structures are called spin networks. They are not sitting inside space, they are space. The smooth, continuous, three-dimensional space you seem to inhabit is an approximation, emerging from an enormous number of these quantum building blocks, the way the smooth surface of a lake emerges from trillions of individual water molecules. In loop quantum gravity, time arises from transitions between one spin network configuration and another. These transitions are discrete quantum events. There is no smooth, continuous flow of time at the fundamental level. Instead, there are individual quantum steps. One configuration of space gives way to another, then another. The sequence of these transitions is what we experience as the passage of time. But at the Planck scale, there is no clock ticking between the transitions. The transitions themselves are all there is. Time, in this framework, is not a fundamental ingredient of reality. It is generated by the dynamics of quantum geometry. It emerges from something that is itself timeless at the most basic level. This has a remarkable implication. If time is emergent, then asking what happened before the Big Bang may be like asking what is north of the North Pole. The question assumes time extends backward without limit. But if time itself is a product of quantum geometric transitions, there may be a point beyond which the concept of before simply doesn't apply. Some calculations in loop quantum cosmology suggest the Big Bang was actually a quantum bounce, a transition from a previous contracting phase where quantum effects prevented the universe from collapsing to a singularity. In that picture, time does extend before the bounce, but time itself may have a fundamentally different character in that regime. The smooth, flowing time we experience may be a feature of our current cosmic epoch, not an eternal property of the universe. String theory takes a different approach. In its most commonly used formulations, string theory is defined on a fixed background spacetime. Time is treated much as it is in standard quantum mechanics, as a parameter along which string vibrations evolve. Strings vibrate in time, they interact in time, they scatter and recombine in time. Time is present and functional in the equations, playing its familiar role as the stage on which physics unfolds. But many string theorists believe this background dependence is a limitation of current formulations, not a fundamental feature of the theory. The full version of string theory, sometimes called M theory, may not require a pre-existing spacetime at all. There are strong hints that spacetime, including time, could emerge from more fundamental quantum mechanical structures. The most concrete version of this idea comes from a theoretical relationship called ADS-CFT correspondence, discovered in 1997. This correspondence shows that a theory of gravity in a particular kind of curved spacetime is mathematically equivalent to a quantum theory without gravity living on the boundary of that spacetime. The boundary theory has no gravitational degrees of freedom, and crucially, it has one fewer spatial dimension. Yet it contains all the same information as the full gravitational theory in the interior, including the information about how time behaves in the curved spacetime. This suggests something profound. If a theory without gravity, living on a lower dimensional boundary, can fully describe a spacetime with gravity in the interior, then the interior spacetime, including its time dimension, might not be fundamental. It might be a derived quantity, reconstructed from the quantum information on the boundary. Time would then be emergent, not built in from the start, but arising from patterns in quantum entanglement and information flow. This idea, that spacetime might emerge from quantum entanglement, has become one of the most active areas of research in theoretical physics over the past 2 decades. And it deserves more attention because if it is correct, it would fundamentally change what we think time is. The insight began with a striking observation made by the physicist Juan Maldacena in 1997, the ADS-CFT correspondence mentioned earlier. But the implications for spacetime and time specifically became sharper in subsequent work. In 2010, the physicist Mark van Ramsdonk published a thought experiment that made the point vivid. He considered two quantum systems that are maximally entangled, meaning their quantum states are correlated as strongly as quantum mechanics allows. In the ADS-CFT framework, this entangled pair corresponds to a single connected spacetime in the gravitational description. The two systems are linked by a region of space. Now, van Ramsdonk asked, what happens if you gradually reduce the entanglement between the two systems? As the entanglement decreases, the spatial connection between the two regions gets longer and thinner, like a bridge being stretched. And if you remove the entanglement entirely, the connection breaks. The two regions become completely disconnected, separate spacetimes with no spatial link between them. The implication is remarkable. Spatial connection, the fact that one region of space is next to another rather than disconnected from it, might be created by quantum entanglement. Space might not be fundamental. It might be stitched together by entanglement between quantum degrees of freedom. And if space is stitched together by entanglement, then the geometry of spacetime, including its time dimension, is a consequence of how quantum information is organized. Not a pre-existing container, not a stage, a product. Leonard Susskind and Maldacena pushed this further with a conjecture they called ER equals EPR. The shorthand refers to two famous physics papers, both coincidentally published in 1935. ER stands for Einstein and Rosen, who described what we now call wormholes, bridges connecting distant regions of spacetime. EPR stands for Einstein, Podolsky, and Rosen, who described quantum entanglement. The ER equals EPR conjecture proposes that these two phenomena are actually the same thing. Every pair of entangled particles is connected by a tiny wormhole. Every wormhole is a manifestation of entanglement. Spacetime connectivity and quantum entanglement are not two different phenomena. They are two descriptions of the same underlying reality. If this conjecture is correct, and it remains a conjecture with strong theoretical motivation, but no direct experimental confirmation, then the fabric of spacetime is literally woven from threads of quantum entanglement. Time, as a dimension of that fabric, would derive its existence from quantum correlations between the fundamental degrees of freedom of the universe. Time would not be built into the foundations of reality, it would be built by reality, constructed from something deeper, something that is itself neither spatial nor temporal, but purely quantum mechanical and informational. This does not mean time is fake. The spacetime that emerges from entanglement is physically real. It curves. It carries gravitational waves. It produces all the time dilation effects we've discussed tonight. But it is emergent rather than fundamental, in the same way that the temperature of a gas is real and measurable, but emerges from the collective motion of molecules rather than being a basic property of any single molecule. Time, in this picture, is what quantum entanglement looks like when viewed from the inside, by beings like us, who are themselves part of the entangled system. Causal set theory, pioneered by Raphael Sorkin and collaborators, offers yet another perspective. In this framework, spacetime is replaced by a discrete set of events, points that are connected by causal relationships. Some events can influence others, some cannot. The pattern of these causal connections, which events are in the causal past of which other events, determines the structure of spacetime. There is no continuous manifold, there is no smooth geometry, there is just a network of events and their causal ordering. In causal set theory, the ordering of events is fundamental. The fact that event A can influence event B, but not vice versa, is a basic feature of reality, not derived from something deeper. In this sense, causal set theory preserves something like time at the fundamental level. The causal ordering is a kind of temporal structure. It tells you which events come before which other events. But the smooth, continuous flow of time that we experience is not fundamental. It emerges from the underlying discrete causal structure when you zoom out and look at the large-scale pattern. The individual events in the causal set don't have coordinates or timestamps. They have only their causal relationships to other events. Time as a coordinate, time as a number you read off a clock, is an approximation that works at large scales but dissolves at the Planck scale. Each of these approaches, loop quantum gravity, string theory, causal set theory, and others including causal dynamical triangulations and asymptotic safety, represents a serious attempt to resolve the conflict between quantum mechanics and general relativity. Each has its own mathematical framework, its own strengths, its own difficulties, and each treats time differently. In some, time is emergent. In others, it is fundamental but discrete. In still others, the question remains open within the theory itself. What they share is the recognition that our everyday understanding of time, as a smooth, continuous, universal flow, cannot survive unchanged at the deepest level of physical reality. Something must give, and whatever replaces our current understanding will reshape how we think about time's most basic nature. But there is another deep puzzle about time that doesn't require quantum gravity to state, even though it may ultimately require quantum gravity to solve. It is the question of direction. Why does time flow in one direction and not the other? Think about what this means. The fundamental laws of physics, Newton's laws, Maxwell's equations of electromagnetism, Schrödinger's equation, Einstein's field equations, are almost entirely symmetric with respect to time. If you take a movie of particles interacting according to these laws and play it backward, the reversed movie also obeys the same laws. A billiard ball collision played in reverse looks perfectly physical. A planet orbiting a star played in reverse is also a valid orbit. At the level of individual interactions between fundamental particles, the laws of physics don't care which direction time runs. Forward and backward are equally valid. There is a very subtle exception involving certain rare particle interactions that violate what physicists call T-symmetry. But these violations are extremely small and don't account for the overwhelming directionality of time that we observe in everyday life. For all practical purposes, the fundamental laws are time-symmetric. Run them forward and you get valid physics. Run them backward and you still get valid physics. And yet, everyday life has an overwhelmingly obvious direction to time. Eggs break but don't unbreak. Coffee cools but doesn't spontaneously heat up. People grow older but never younger. Buildings crumble into rubble, but rubble never assembles itself into a building. Memories exist of the past, but not of the future. You can remember yesterday, but not tomorrow. Every aspect of ordinary experience screams that time has a definite direction, a one-way arrow pointing from past to future. Where does this arrow come from if the underlying laws don't prefer one direction over the other? The answer, or at least the best answer physics currently has, involves a concept called entropy. Entropy is a measure of disorder, or more precisely, a measure of the number of microscopic arrangements that correspond to a given macroscopic state. A neatly arranged deck of cards has low entropy because there is essentially one arrangement that counts as perfectly ordered. A shuffled deck has high entropy because there are trillions upon trillions of arrangements that look equally disordered. The second law of thermodynamics, formulated by Rudolf Clausius beginning in 1850 and expressed in terms of entropy by 1865, later given a statistical foundation by Ludwig Boltzmann, states that entropy tends to increase over time. Disordered states are overwhelmingly more numerous than ordered states. So if you start with an ordered arrangement and let it evolve randomly, it will almost certainly become more disordered, simply because there are so many more ways to be disordered than to be ordered. An egg falling off a table and shattering on the floor is a transition from a low entropy state, an intact egg, to a high entropy state, egg fragments scattered across the ground. The reverse process, fragments spontaneously assembling into an intact egg, would decrease entropy. It is not forbidden by the fundamental laws of physics. Every individual molecular collision in the reverse process obeys Newton's laws perfectly, but it requires a spectacularly unlikely coincidence of molecular motions. Every single fragment and droplet would need to move in exactly the right direction, at exactly the right speed, at exactly the right moment. The probability of this happening by chance is so astronomically small that it would never occur in the observable lifetime of the universe. This is the thermodynamic arrow of time. Time appears to flow from past to future because entropy increases from past to future. Ordered states evolve into disordered states, and this directionality is what gives time its experiential one-wayness. It is why causes precede effects, why we remember the past and not the future, why things age and decay and fall apart. The arrow of time is an arrow of entropy. But this explanation raises a deeper question. Why was entropy lower in the past? The second law says entropy increases toward the future. That explains why things become more disordered as time progresses. But it only works if you start from a state of lower entropy. Run the second law backward, and entropy should also increase toward the past. In other words, the second law alone doesn't explain why there is a direction to time. It only says that disorder increases relative to whatever initial condition you start from. The real question is why the initial condition, the early universe, had such extraordinarily low entropy in the first place. The early universe, shortly after the Big Bang, was in a state of remarkably low entropy. The matter in the universe was distributed almost uniformly. Smooth, hot, dense plasma spread across all of space, with only tiny fluctuations in density, about 1 part in 100,000. This might seem like a disordered state because everything is mixed together, but gravitationally, it is extraordinarily ordered. When gravity is in play, a uniform distribution of matter is a low entropy state, because gravity wants to clump matter together. Clumpy configurations with stars, galaxies, black holes, and vast empty voids between them are higher entropy states gravitationally. The history of the universe since the Big Bang is largely the story of gravity pulling matter from an initially smooth distribution into increasingly clumpy configurations. Stars form, galaxies form, black holes form, entropy increases. And this gravitational clumping is what drives most of the entropy increase we observe in the universe. But why was the early universe so smooth? Why was its entropy so low? This is what Roger Penrose has called the past hypothesis. It is a boundary condition on the universe, an initial state of low entropy that is assumed rather than derived. The laws of physics do not explain why the initial entropy was low. They are equally compatible with high entropy initial conditions, which would produce a universe in thermal equilibrium where nothing interesting happens and there is no arrow of time. The fact that our universe started in a special low entropy state is one of the deepest unexplained facts in physics. Penrose has suggested that a complete theory of quantum gravity might eventually explain this initial condition. But no one has achieved that yet. To understand just how special the initial condition of our universe was, consider a calculation Roger Penrose performed. He wanted to quantify how unlikely the low entropy initial state of the universe is compared to all the possible states the universe could have started in. The answer he arrived at is one of the most staggering numbers in all of physics. Penrose estimated that the probability of the universe starting in a state as ordered as the one we observe is approximately 1 in 10 to the power of 10 to the power of 123. That is a number so large it defies every analogy. It is not merely astronomical, it is beyond astronomical. The total number of atoms in the observable universe is roughly 10 to the 80th power. That is an enormous number. But 10 to the power of 10 to the 123 is so much larger that writing it out in ordinary notation, even using every atom in the observable universe as a digit, would be nowhere near sufficient. You would need more atoms than exist in the observable universe just to write down the number of zeros. What this number means is that the initial state of the universe was not just somewhat special. It was special to a degree that appears almost impossible to account for by chance. If you imagine randomly selecting a starting condition for the universe from all possible starting conditions consistent with the laws of physics, the probability of landing on one as ordered as ours is effectively zero. And yet, here we are. In a universe that did start in that extraordinarily special state, a universe where entropy was low enough at the beginning for the second law to produce everything we see, every star, every galaxy, every planet, every living creature, as entropy has climbed toward its maximum over the past 13.8 billion years. This is why the past hypothesis is so troubling. It is not a derivation from the laws of physics. It is a brute fact about our universe that the laws of physics do not explain. The laws tell you what happens given an initial condition. They don't tell you why the initial condition was what it was. Some physicists accept this and treat the low entropy beginning as simply a boundary condition, an observed fact about nature that we incorporate into our models without further explanation. Others find this deeply unsatisfying. A fact this improbable, they argue, cries out for an explanation. There must be some mechanism, some deeper principle, some feature of quantum gravity that we haven't discovered yet, that makes the low entropy beginning not just a lucky accident, but a necessary consequence of the fundamental theory. If such a mechanism exists, it would do more than explain why the universe started the way it did. It would explain the arrow of time itself. It would explain why eggs break and don't unbreak, why we remember the past and not the future, why everything ages and decays. It would ground the most obvious feature of our experience of time, its directionality, in the deepest laws of physics. And it would likely require exactly the kind of theory we don't yet have. A complete theory of quantum gravity that describes not just how space-time behaves, but why the universe began in the particular state that set time's arrow in motion. Arthur Eddington, the British astrophysicist, once wrote that the law of increasing entropy holds a supreme position among the laws of nature. He argued that if your theory contradicts the second law of thermodynamics, it is in deep trouble. The arrow of time, rooted in entropy, is one of the most robust features of our observed universe. And yet, at the fundamental level, the laws that govern individual particles don't have this arrow. The directionality of time is not built into the fundamental equations. It emerges from statistics, from the overwhelming probability that disordered states follow ordered states, combined with the unexplained fact that the universe began in an ordered state. This distinction between the fundamental laws and the emergent behavior is crucial for understanding what time really is. At the deepest level, time as described by the fundamental equations of physics may have no preferred direction. Forward and backward may be equally valid. The arrow we experience, the sense that time flows from past to future, may be a large-scale statistical phenomenon. Real and physical, but not fundamental. It would be like temperature. Temperature is real, you can measure it, it affects physical processes, but it is not a fundamental property of individual particles. A single molecule doesn't have a temperature. Temperature emerges from the collective behavior of enormous numbers of molecules. The arrow of time might be similar. A single particle interaction doesn't have a temporal direction. The arrow of time emerges from the collective behavior of enormous numbers of particles, starting from a low entropy initial condition. This brings us to a question that people inevitably ask when they learn about the physics of time. What about our experience of time? We don't just measure time with clocks and equations, we feel it. We perceive a present moment, a now, that seems to move forward through time. The past feels fixed and settled, the future feels open and undetermined. We experience time as flowing, as passing, as carrying us from one moment to the next. Is this experience reflected in the physics? The honest answer is that it is not. At least, not in any way that current physics can explain. The equations of physics, whether Newtonian, relativistic, or quantum, do not contain a now. They do not describe a special present moment that moves forward through time. In relativity, all moments are equally real. The past exists, the future exists. Space-time is a four-dimensional block containing everything that ever happens and everything that ever will happen. There is no fundamental distinction between past, present, and future. Einstein himself, after the death of a close friend, wrote that the distinction between past, present, and future is only a stubbornly persistent illusion. This is sometimes called the block universe picture. Space-time is a complete, four-dimensional structure. Every event that has ever occurred, and every event that will ever occur, is part of this structure. Nothing flows, nothing moves through time. The block just exists, eternal and unchanging, containing all of history at once. But this picture is difficult to reconcile with our experience. We don't feel like we're living in a frozen four-dimensional block. We feel like we're moving through time, experiencing one moment after another. The present moment feels special. It feels real in a way that the past and future do not. How do you square this subjective experience with the physics? One possibility is that our experience of temporal flow is a product of how our brains process information, not a feature of external physical reality. Our brains form memories of the past, but not the future. This asymmetry, rooted in the thermodynamic arrow of time and the increase of entropy, creates the sensation that time flows from a remembered past toward an unknown future. The feeling of flow might be what it's like from the inside, to be a physical system that records memories and increases in entropy. It would be a real experience, but it wouldn't correspond to any objective flow in the external world. This is not the same as saying time is fake or that time is an illusion. The physical effects of time are entirely real. Clocks tick at different rates. Astronauts age differently from people on the ground. Muons live longer at high speeds. GPS satellites require relativistic corrections. These are measurable physical facts. What may be less fundamental than it seems is the particular way we experience time, the sense of a flowing present, of a past slipping away, of a future approaching. That specific experiential quality may be a feature of consciousness and neurobiology rather than a feature of fundamental physics. It is important to draw this distinction carefully. Physics has shown us that time is not what common sense assumes. It is not universal. It is not absolute. It runs at different rates in different places. It may be emergent rather than fundamental. It may have no preferred direction at the level of basic laws. These are established results, supported by overwhelming evidence. But physics has not shown that time doesn't exist. It has not shown that change is unreal. It has not dissolved time into nothingness. What physics has done is reveal that time is far more subtle, far more complex, and far more strange than we ever imagined from our everyday experience. And the deepest questions remain open. Does time emerge from something timeless? If so, what is that timeless substrate? Is the flow of time an objective feature of reality or a subjective feature of consciousness? Why did the universe begin in a state of low entropy? Will a theory of quantum gravity resolve the problem of time, or will it deepen the mystery? These questions are not philosophical abstractions. They are precise physical questions with potential empirical consequences. future observations of the cosmic microwave background radiation, future detections of gravitational waves from the early universe, future experiments probing quantum gravity effects. Any of these could provide evidence that constrains or resolves these questions. The answers are out there, encoded in the structure of the universe, waiting to be found. What we know with certainty is this: the time you experience in your daily life, the uniform ticking of clocks, the sense that everyone shares the same flow, is an approximation. An extraordinarily good approximation for the conditions of your everyday existence, but an approximation nonetheless. Beneath that surface lies something richer and more strange than any human civilization imagined before the 20th century. Time depends on how fast you move. Time depends on how strong the gravity around you is. Time may emerge from something deeper. Time may have no fundamental direction. And the final answer to what time really is remains one of the greatest open questions in all of science. We began tonight with something that felt like the most obvious fact in the universe: that 1 second for you is 1 second for everyone else. That time flows at the same rate everywhere. That there is a single universal clock ticking away in the background, carrying all of us forward together. We've seen, step by step, that every part of this picture is wrong. Not slightly wrong, fundamentally wrong. Time is personal. Time is local. Time is shaped by the path you take through space-time. And the deepest nature of time remains a mystery that the greatest minds in physics are still working to unravel. The next time you glance at a clock, remember what you've learned tonight. That clock is not showing you universal time. It is showing you your time. The time accumulated along your particular path through the universe, shaped by your particular speed and your particular gravitational environment. Someone else, somewhere else, moving differently, sitting at a different depth in a gravitational field, has a clock that disagrees with yours. Neither clock is wrong. Neither clock is broken. They simply measure different things, because time itself is different along different paths through space-time. You carry your own time with you wherever you go. It belongs to you, and to your path through the universe, and to no one else. The universe does not have a master clock. It has as many clocks as there are paths through it. And what ties all these different times together, what unifies them into a single, coherent picture, is not a shared flow, but a shared geometry. The geometry of space-time, described by Einstein's equations, curved by mass and energy, connects every path and every clock into one consistent mathematical structure. Time is part of that structure, not separate from it, not above it, woven into it. Physics has not finished with time. The story is still being written. Somewhere in the mathematics of a theory we haven't completed yet lies the answer to what time truly is at the most fundamental level, whether it is an ingredient of reality or a product of it, whether it is the river that carries us or the landscape we create by walking. Whatever that answer turns out to be, it will change our understanding of the universe as profoundly as Einstein's revolution changed it a century ago. And it will begin, as all great discoveries do, with the willingness to question what seems most obvious, even something as familiar as the ticking of a clock. Thank you for joining me on this journey tonight. If you found this exploration meaningful, a like or subscribe would mean a lot. It helps me keep making these deep explorations of how the universe actually works. Sleep well, and remember, every second that passes for you is yours alone. Your time, shaped by your path through the cosmos. And that, more than anything, is what makes time so extraordinary.